Hello all. I think we're experienced many different types of lecture delivery. um, so we're going from me having to wear a mask to I'm now delivering them at home. So well, there we go. We'll just keep working through this as best we can. I will be trying to record these and have these up by the usual lecture time each week. Feel free to send me questions as usual as we go forward. So this one is a bit of a change of pace. I thought it might change of pace, and it'll also be beneficial for a couple of the assignments that are there, especially Mount Mag. Today I'll talk a bit about orthomagmatic deposits. This will be in 2 installments, fairly short lectures. Tomorrow I'll talk about superficial deposits to help with that superficial deposit practical as well. So we're jumping a bit out of the sphere of hydrothermal systems just for a little while, just to keep you engaged and away from the constant hydrothermal behaviour, and we'll move towards some magmatic systems. So once I get this working. Okay, so introduction for this one, we're going to look at magmatic or orthomagmatic. I generally settle on magmatic deposits, and these are associated with magmatic processes, hence the name. It's not overly imaginative, but they don't involve hydrothermal fluids. So this is where they're slightly distinct. The hydrothermal system, as we've discussed, is usually the late stage fluids egressed off magma systems in late magmatic deposits. This we're looking more at what happens in the silicate liquid or the magma. So the kind of examples we're looking at might be nickel sulfide or PGE deposits. So nickel sulfide deposits are becoming quite important now with the high demand for nickel. Nickel prices are very good, so nickel mines are becoming very important because they're used a lot in these batteries and EV vehicles. So Elon Musk is quite keen on these. Another style is chromium deposits, and then in the second component of this lecture, I'll talk about very weird rocks called carbonatites. They're very unusual, and they can house rare earth element deposits. Then look at a few types associated to diamonds, kimberlites and lamproite association. So they're really the pipes or the material that brings the diamonds up from very high pressures. And finally, pegmatites, which we've discussed a little bit, which are very important for a variety of different commodities, particularly lithium at the moment, but also things like gems, beryl, aquamarine, very common in pegmatites. So to start with, nickel sulfide and chromium deposits. Okay, so magmatic processes. Orthomagmatic deposits form within the magma chamber, and they're associated to the crystallization of minerals. Okay, so we have to consider those dynamics, which are going to be controlled by its composition, its pressure and temperature conditions, how much water is there in the liquid, and things like that. So the processes that have become important are fractional crystallization, just taking you back to the first trimester or last year about how magma compositions can change when you crystallize minerals out of that system. Water saturation, so this is just when water concentrations get to a position where they're so high that they will enable water to form. Miscibility, fancy way to say unmixing. Think about oil and water. They don't mix completely. The oil will congeal and form a separate fluid phase when it's with water. Gravity separation, this links strongly back to fractional crystallization, about how we can separate minerals or maybe liquids based on different densities. Late stage crystallization, the final products, which can be water rich. And finally, contamination or assimilation. This is just where the magma interacts with surrounding host rock, country rock, and dissolves material in it, helps to change its composition. Most of these processes happen in pretty much every magma body, but in some cases they lead to a concentration of metals to form an ore body. So again, we're looking for where does nature do our work for us, and what is controlling that effort of nature. Okay, so the physical chemical controls, like I mentioned, we have pressure and temperature as always, how hot it is, what depth it's at. We have what kind of tectonic associations. We've discussed that briefly during week 2 about where certain magmas will form and how that relates to certain styles of ore bodies. Subduction zones, very common to have copper and potentially gold style mineralization. Cratons, more likely to have your kimberlites, lamprolites to form your diamonds, etc. The viscosity of the magma, which links back to its composition and its content of water, so how easily it flows. The size always matters when it comes to an ore body. So, this can also influence concentration. And then we have a few other things like convection, but partition coefficients is quite important. It's just a way to describe how the elements are moving between the minerals, certain minerals, and the liquid. So, essential features of a magmatic ore body. So it forms at high temperatures while the magma is still predominantly liquid. And so we haven't led to significant crystallization. Remember, it's a spectrum. We start at the liquidus, so we go from fully liquid, 100% liquid, down to the solidus, which is 100% solid, and we need to be at that higher end where we have predominantly liquid. So enrichment process need to concentrate low metal values to locally high values. So it can be very sporadic, and we want to find what can control to get us those high grades. And this enrichment occurs as the system evolves and the partitioning of elements or minerals or gravitational separation can drive us to a position where we can concentrate particular metals. In this case, the commodity can separate as a melt or as a liquid, and I'll go through that liquid in a little bit. Okay, so nickel sulfide deposits, quite a common style in Australia. These are hosted in ultramafic rocks, so they're very common in the Archean. Okay, and the reason for that is that in the Archean we had high geothermal gradients in the mantle, so we could actually produce ultramafic lavas at temperatures of like 600 degrees. These are called komatiites, fancy word, and they're very common in Western Australia. Some of our Western Australian students might have seen them, or others might have seen them. And they're very hot, high magnesium lava flows. And then as the mantle has progressively cooled, komatiites are no longer a common lava that forms. People think they might be forming these days, but it's not that clear that they are. And so they're very common here in these lavas. Other ones can be formed in thick mafic to ultramafic intrusive complexes like Duluth or Nolinsk. And in the Yilgarn, there is evidence that komatiites have essentially erupted over basalt falls and caused erosion because it's so much hotter than the basalt. And these hollows actually contribute to the accumulation of metal sulfides when we go into this liquid immiscibility. So in essence, we have an unmixing of a sulfide rich liquid versus a silicate liquid, or what we generally perceive to be a magma. So here's an example of what happens. We have these orange dots. Here are these high sulfur melts within something like a komatiite. So what happens is the high sulfur melts don't mix easily with the silicate liquid. So they actually separate into their own little globules. Okay, so this is called what we call a miscibility. So we're getting this unmixing of the two liquids. And this happens generally when the sulfur gets to a position of saturation. So the sulfur concentrations are so high that it then wants to create its own liquid distinct from that magma. What happens is these little globules are quite dense, 4.5 versus whatever the magma is, probably 3.4 or 5, and they actually settle via gravity, and they will actually pond in the bottom of these lava flows, or maybe into a magma chamber. And the sulfur actually takes with it many metals like iron, nickel, and the PGEs, and they are separated from the magma into that sulfur globule, and then they can concentrate at high grades in these sort of sheets or sequences within the lava flow. So this is an example of a liquid miscibility style deposit, and common examples can be Sudbury, Canada, Norilsk in Russia, Voisey's Bay in Canada, Duluth in the US. And so it's quite an important way to concentrate certain metals. So here's just showing where some of these important provinces are, and as you can see, they're predominantly where we have large cratonic lithosphere. So Western Australia, Africa, Brazil. Over here we have the Canadian shield, and the big shields in Russia. So that's largely because we get these magmas that are hot enough to contribute to this process. And a bit closer to home here is in Western Australia, as I mentioned, the many komatiites. The stars here represent common nickel deposits. So Kambalda might be one of the biggest ones down here. We also have Agnew Luna up here, and a few other ones down towards Southern Cross. This is where most of Australia's nickel is, and there's sort of green schist facies, metamorphosed komatiite volcanic rocks. So here's just an example of the sort of size and grade of different global resources of nickel ore. So we have nickel copper sulfides associated with komatiites in this purpley colour. Here's Kambalda, high grade, quite a large ore body, and Perseverance, another one in Western Australia, is also quite big, and a few others, Mount Keith. So there's quite substantial world-class ore bodies. We can also get basinal nickel copper sulfides in intrusive bodies such as Duluth, Norilsk, Voisey's Bay, like I mentioned, and then we can also get other styles like Sudbury. So what is the nickel sulfide deposit? Here's an example. I think we've shown this one before. We have pale pentlandite blebs. So pentlandite is a nickel sulfide within yellow chalcopyrite. So it looks like chalcopyrite. Here's the pentlandite, and this darker area is pyrrhotite. So an iron sulfide intermixed with nickel sulfide and copper sulfide. So what happens in these systems, we get this massive sulfide ore when we have this accumulation. We need very high temperatures. So at the highest temperatures of magma, sulfur is soluble in the silicate melt. It's happy, it will stay as a silicate liquid. The sulfur gets into those magmas largely from either the mantle or from the seawater through contaminating with marine sediments. And then upon cooling, the solubility of sulfur decreases in the silicate liquid. And then eventually it reaches a point where it's saturated, and it no longer wants to be in the liquid. It wants to form its own sulfur melt. So this is what happens. Then we can partition in with it certain metals that prefer to bind with sulfur. They complex with sulfur, and then it can accumulate. So In these Western Australia deposits, the sulfur might have been assimilated from rocks that melted when the lava erupted over the surface. So it's incorporated that way. It might not have been in the primary magma. And people have argued, and this argument continues, that komatiites might have formed in tectonic settings akin to subduction zones. Remember, the tectonics in the Archean is less clear, so this is still openly debated. And it's very important that sulfur saturation occurs early in the magma crystallization history before substantial crystallization, because it will actually certain phases will take away those metals and make the deposit of lower grade. So it occurs during this contamination. Upon saturation, sulfur separates. If it does not occur early, nickel will partition into olivine and be lost. So this is what I'm saying. It has to occur before olivine crystallization, which usually is one of the early crystallizing phases in high magnesium ultramafic lavas. And then we need to get the sulfur saturation up very quickly. In which case, if there is a sulfur liquid, nickel prefers, or it petitions, petition coefficient is higher to the sulfur liquid than it is into olivine. It will also then scavenge chalcophile elements such as nickel, iron, copper, and the PGE. So then what happens if it's in a komatiite fire? The massive sulfide pods sink into the hollows created by this thermal erosion. And then above this, you get what we call a neck-textured sulfides, and then finally down to seminified false sulfides as you move further up, indicating progressive changes in the crystallization of the melt. So we're getting to points where we're crystallizing more minerals and less of the sulfur. And then at the uppermost parts of the flow, we're sulfur poor, and we're just into a standard sort of komatiite. So here's a nice picture. Here's our nice massive sulfides that I showed before. We move into a neck texture. You can see we're getting largely mafic or ultramafic lava intermingled, and as we go further this way, we get into less sulfides and more into a classic komatiite. Okay. The second deposit I'm going to talk about is chromite deposits. So slightly different to sulfides. They're not immiscible. This is more of a classic fractional crystallization or accumulation behavior. And the most famous example is something like the Bushveld complex in South Africa. So chromium is highly compatible in spinel minerals. Magnetite is a spinel mineral. You've probably heard of other ones. But you know, probably one of the most common one is a luminous spinel or spinel. It also petitions into pyroxenes because it likes to behave a bit like magnesium. When mafic and ultramafic magma is contaminated by felsic melt, the chromium becomes incompatible and will precipitate as chromite, so an iron chromium spinel. In some cases, monomineralic crystallization takes place, leading to concentration of chromite only. So what this means is we start with our magma, we can start crystallizing early chromite, potentially, if the conditions are right. Chromite is very dense and it should settle. And then if we're lucky, it crystallizes before, say, pyroxene, and then we can produce pure chromatite layers. Okay, and then as we progress, the magma composition changes and we start to crystallize different phases. Potentially the chromium is depleted or it is now hosted in pyroxenes or other phases as we cool, but we're producing this high concentration of chromium in these layers. So, like I said, a chromite just sinks to the bottom. We're super imaginative and we call this rock a chromatite. And so most chromite occurs in these cumulate zones and might be interspersed with silicate minerals like anorthite, pyroxene, and olivine. And this is associated to these mafic magmas. In things like the bushveld, we get rhythmic layering, and it's still highly debated how this forms. People think you might get individual convection cells disrupting those layers and enabling gravitational layers to separate and form distinct high density layers on top of each other. We can also get potiform deposits which taper at the margins, and these systems can, as always, be faulted and disrupted. Oops, sorry. So here's a beautiful example. It's like the bushveld, where we have these dark chromite-rich layers, this big fault, and we might have them dispersed with pure white anorthosite. This might be closer to the host gabbro or gabbronorite, and we have other layers which are rich in pyroxene cumulates. So what we can form is these beautiful, what we call cumulate textured rocks. So they're a layered magmatic intrusion where we have chromite forming a sort of connected texture where all these crystals have fallen into a dense layer, and we actually have white areas here which has actually been transformed to talc, largely through low-grade metamorphism and alteration. And this represents the little interstitial bits of liquid left between these crystals as they accumulated. This example is from Barabra, and you have one in your rock hit, so it's worth having a look at. And like I said, the classic example is Bushveld, world's largest chromium deposit. We also have the Stillwater, but we have little ones, more potiform style in the Great Serpentinite Belt, where we have these ultramafic intrusions. So that's all for that one there. Thank you.